lovely introduction. And hi, everyone. This is working? Okay, good. Yeah, so my name is Nikhil Barthwal. I'll give a talk about microservices and implementing them as a serverless application. I guess serverless is like kind of a new hot topic these days. But before I actually go to serverless, I want to bring it back to microservices, and I want to basically highlight the point of why we actually moved to microservices, right? So we started with monolith. We know monolith was simple, easy to deploy, one big application. But as the scale of the application grows, it becomes harder to test, harder to deploy. It basically stops the innovation, right? We can't deliver the products fast enough in the market. So we decided to move to microservices, which is, well, rather than having one big service, we fragment it into small parts. We know microservices have several advantages. Well, we have independent releasability, better scaling, so now we can release these services independently. What that means is the velocity of innovation actually is increasing. We have technology heterogeneity, so we can implement services in different languages, different frameworks. We are not restricted to one. We obviously have resilience, although moving to microservices might increase the frequency of failures at times because you have more moving parts in the system. The scope of those failures now is reduced because if one service fails, it doesn't affect the remaining service, right? And we obviously have ease of migration in the sense that if I want to migrate my system down the line, I can do it bit by bit because I have these loosely coupled services which I can, migrate one by one without having to worry about like one big migration process. So there are like several advantages, easy to test, easy to deploy with microservices. But the point that we got to understand is that microservices has a bad aspect to it. Like everything in life, you have some good aspect, you have some bad aspect. And there are numerous problems with microservices. So for example, I kind of highlighted about it, but if we have more moving parts, then we have more complexity in the system, and more complexity means more chances of failure. Microservices does increase the frequency of failures, generally. Obviously, like I mentioned, there's a better resiliency, so if one service fails, it doesn't affect the remaining services. So yes, the scope of the failure is reduced, but the frequency of that failure is actually more. There's more need for automation, right? Because when you had this one big service, you don't actually need kind of automation. It's just you can have everything manually, just one click of a button, automate. But now imagine you have a system with 1,000 microservices, right? And you need a whole lot of CI/CD pipelines and automated testing. Integration testing becomes a challenge. There's a lot of need for automation, which basically is what I would call as something like an undifferentiated heavy lifting that you have to do. Deployment becomes a lot more complex because now you have to deal with a scenario where you have a partially failed deployment. I'm deploying 1,000 services, 990 worked fine, 10 failed. So there's a problem. It's not all or nothing. You kind of have a partial failure into the picture. Testing obviously can be a very cumbersome thing with microservices, especially integration testing. Unit testing, not so much. So essentially, when we move from monolithic to microservice, we trade one set of problems for another one. Most notably, what we do is we increase the frequency of velocity of innovation, but at the same time, we bring in more complexity. That's the problem with microservice. So let's actually now move to serverless computing and see if serverless computing can help us a bit here. So I'll start by definition. Right? What is serverless computing? This is a textbook definition, but essentially serverless computing is you have these small functions, right? Different people have different names. If you're talking about AWS Lambda, we'll talk about some of the commercial offerings here, but you have these functions that are triggered by certain input and output binding, right? There are major AWS as AWS Lambda. We also have Azure Function from Microsoft, Google Cloud Functions. They're all very mature now. They're widely available. A lot of people use them. There are obviously differences between various offerings for cloud, but you have them. And what serverless application model basically is that similar to microservice, you have your applications in form of small functions, all right? So you have these functions that they have a certain input and output binding, and whenever the state of that input binding gets changed, the events get triggered. So it's kind of an event-driven architecture here. And the point is that these functions are supposed to be small granular unit. So most of the cloud providers would put some limits on the amount of resources you can consume. The limits on those resources would vary from cloud provider to cloud provider, but the point is that you should have small functions, small granular functions. And they mostly support asynchronous execution flow. Now, again, I'm highlighting that this is the general what serverless computing is. Depending on your provider, things can vary a little bit, but that's where the general idea is. So it's often called as function as a service, or FaaS, as you call it. And when we actually compare microservices and serverless, there are some similarities. And the similarity is that on the microservice side, we have this application that consists of fine-grained services, right, through which we are providing services. And on the serverless side, we have this logic distributed in stateless event-driven containers. But what is common among both these approach is that your application is fragmented as basically loosely coupled components, which leads us to the next insight that we have, that we could potentially implement the microservice architecture as a serverless function. So let's actually dig into this topic now. So when you look at microservices and monolith, what you observe is typically you will have like one machine with, operating system, runtime, dependencies, application, whole stack. You obviously want to scale it, so you have a second machine. There's some bits of auto scaling. You have a load balancer. Everything good. The problem with this architecture is that while you have bits and components available to you, you have a load balancer in AWS, you have an ELB, you actually have to configure and hook up everything yourself, right? So there's a lot of undifferentiated heavy lifting here. You're not implementing it from scratch, you're not implementing a load balancer, you're not implementing auto scaling, but you still have to configure it. That's amount of work for you. So, you have to have scaling up, service discovery, and so on. What that means is when you implement microservices in the standard way, you have a lot of management overhead that you have to deal with it. Whereas, when you go into the serverless application, things look a little different. So, you have an abstraction of servers. Common misconception, serverless computing does not mean you don't have servers. You do have servers. It just means you don't have to manage them. Right? A lot of people get confused with this. So servers are abstracted for you. Right? It's an event-driven scale. So all that availability, all auto scaling, everything is handled for you. And it's a sub-second billing, more like a pay-as-you-go model. So all that done for you, what that means is you have less management overhead. So the key point I'm trying to make is by implementing microservices as a serverless, you get a lot of advantages that you get with microservices in general, but you avoid a lot of management overhead. That's the advantage of implementing microservices as a serverless advantage. You just eliminate all that undifferentiated lifting or management overhead that you have to do. But here, let's actually dig into this a little more. What are we talking about? Let's look at the big picture. Am I saying, well, you have to choose between serverless and microservices? Turns out that's not the case. Most real-life systems actually use both. And while there are advantages of moving to serverless, there are obviously certain disadvantages, right? So what are those disadvantages? Well, you have the benefit that it's cheaper to operate because it's sub-second billing, more pay-as-you-go. You have less management overhead. The problem with serverless is you only support asynchronous method of communication. So what if you want synchronous method? The second thing is you have a resource limitation, right? You can't have a long-running process as serverless one function. I mean, you can split it in many functions, yes, but you can't have one function doing a lot of work. I think AWS puts a limit, might be, I think 5 minutes or 7 minutes, or there's some kind of limit like that. I don't know exactly, but it's around that figure. Whereas with microservices, you obviously have an advantage that it's always on. There's no cold start. So basically, when you have a cloud function, right, and when you're using it, it boots up. But when you're not using it, it basically shuts down. And the next time you boot up, it has to start. So there's a latency involved that's called as cold start. You don't have any cold start in microservices. It's always on, right? You deploy it, it's there, your container is running. There are no resource limitations. There are drawbacks. It's always on, which means it's more expensive. And we know that there is more management overhead. So typically, a real life system would have parts of it implemented as serverless and parts of it implemented as microservice. Rarely do we have systems that are 100% serverless. So there's a hybrid approach. And what are the parts that you want them as microservice and what are the parts that you want them serverless? Let's actually dig into that. So let's look at some communication patterns that we have. Okay. Typically, we can divide the services in, I like to call it 3 tiers, although you can have 4 or 5 depending on how you want to classify them. You have a directly customer facing tier, then you have something that affects customers indirectly, and then you have little to no impact on customers. For example, let's say you're running an e-business, say Amazon or something. If your front end is down, the customers can't place an order. So your system is basically unusable by end user customer, right? That's a tier 1 service. It impacts the customer pretty much directly, like you can't just use the system. Then you have a tier 2 system, for example, order processing. If that system is down, your order gets delayed. They get delayed, but it's not like they get canceled. So it does impact you in the sense that if you have a 2-day delivery, you might get that order, I don't know, in 3 days or something like that. So there's an impact, but it's not like terrible. And then you have a, tier 3 systems, for example, logging, monitoring, and all those that gives you visibility to your system. If the logging service for Amazon is down, I as a customer, I don't care. It doesn't impact me at all. And typically how we do it is, the first tier is usually a request response. It's more synchronous. And the reason why we need this to be more synchronous is because we need better error control. Remember, we can't afford to have downtime on tier 1. And the disadvantage with asynchronous communication is that let's say one tier 1 service calls another tier 1, it sends an asynchronous message. It doesn't know what happened after that. There is no visibility to that message, right? I send a message, hopefully it gets processed. If not, I don't know what's happening. Whereas with the synchronous, I send a message, I get an acknowledgement back, I get a response back. The processing could be delayed, but at least I know that, okay, the message was received, yes, it was acknowledged. So there's a lot better error control because if something goes wrong, I know it went wrong, I can take action. So tier 1 services generally tend to be more synchronous nature, which means they cannot be actually serverless because serverless traditionally supports only asynchronous. So that's one case. Whereas, and that's the reason why what we tend to do is this tier 1 is almost always a microservice. Now, there's a little bit of controversy here. I showed this slide to someone and he was protesting, you're wrong, I disagree with you. I'm like, why? Well, I could have a service that is always on yet serverless. Yes and no. At a theoretical level, the answer is wrong because serverless only supports asynchronous. But what happens during the implementation level is a lot of vendors, they actually give you an ability to have an always on container and they package it as a serverless. So the line between what is a cloud is a serverless function and what is a microservice running is actually a little blur when you talk about implementation. For example, Azure has something called Azure App Service, which is essentially a container where you can run a function. And that runs 24/7, right? There is no pay as you go, there is no cold start, nothing. But at the same time, they package it as a serverless, but in my world, it's actually doesn't fit in a serverless definition. It's just a microservice because it's at that point a container. All they have done is they have hooked up the container with an input-output binding of the Azure Service Bus. So again, when it comes to implementation, the difference is the line gets blurred between what is function and what is actually a microservice. But typically, tier 1 generally tends to be microservice because microservices can communicate by synchronous and they have to be always on. You need near 100% reliability, something like 99.99, whatever your uptime goal is. Whereas tier 2 and tier 3, you can have them as event driven. Event driven are better, cheaper to operate and so on, but you do have problems with cold start in the sense that there could be latency involved in it. So tier 2 and tier 3 actually can be implemented as an event driven, and they make excellent candidates for serverless application. In companies that generally don't use serverless, what they tend to do is they have like a message bus like Kafka. So they'll have their tier 2 and tier 3 services reading and writing messages to Kafka topic. If you're talking about serverless, you can actually replace all the services as cloud functions, and cloud's provider usually would provide you a service bus. So you would not be using Kafka, you actually would be using the service bus provided by your service provider. I'm going to expand a little bit. There is one drawback that serverless computing has, that it's not very standard. As a result of it, you don't have one message bus that for all different vendors there has to be a little bit of a vendor lock-in or vendor specific service bus that you'll be using. But nevertheless, you tend to have a service bus, and tier 2 and tier 3 generally would be implemented as serverless functions. So they are serverless functions. Now, when we talked about moving from monolithic to microservices, we talked about the fact that distributed functionality actually leads to faster innovation. That is because more loosely coupled execution unit, what they can do is they reduce your team interdependencies, right? And when you have less team interdependencies, what that means for you is faster innovation. That's the reason why when you move from monolithic to microservice, you actually experience an increased feature velocity because you have distributed functionality. And you look at the trend, you had the monolithic, you had the microservice. Serverless is just one step beyond that. So it's basically an extension of a trend that we are already seeing in the market today. So when we talk about serverless computing, what we are doing is we are handing over a lot of resource management, right, to the vendor. So we had this IaaS PaaS, they are vendor managed and fast. They really would take your application and a lot of underlying stuff, and they will manage for you. What that means is, the good news, you have less infrastructure to worry about, but at the same time comes with a drawback that when you're handing the control to somebody else, you're losing control. So you have less control on your part. Usually that is not a problem, but there are times when they become, and if they do, serverless computing is probably not the best way to go forward. So let's talk about anti-patterns here, common data ownership. Now we know that in the microservices world, what they recommend is that each service should have its own database, right? So you have a database to each service, you don't share the database, and you have a well-defined interface to that service through which they communicate. That kind of pattern extends to the serverless applications also. So what you don't want is, you typically would have a backend as a service, you would have your tables, and you have all these functions. You don't want something like this. This is an anti-pattern, because what it does is it increases the coupling. So if I want to change a schema for first table, I would have to change a lot of functions in an incoherent manner, and that introduces more coupling for me. More coupling means more team interdependencies, less innovation. So in a way, I have basically defeated the purpose of moving to serverless application, right? I want the serverless because I can innovate faster. And here, if I use something like this, I can't do that. So how it works is that what you want is, you want the schemas to be isolated across the team. So you want your backend as a service, you have these tables, and then you have these different teams. Typically, one team will own more than one functions. In microservice world, usually that's the case, but it's not necessary. And the reason why it's not necessary is because microservices don't have a resource limitation. Serverless do. So the chances that the functionality that one team is required for, it might not be possible to implement everything in one function. So more practical scenario is, a team owns a certain functions and it owns a certain schema. And then each of these would have access to this table. So this is basically the serverless view of how data is shared across functions. And when you choose this model, there is one constraint that you're introducing, and that is deployment of a function. Here it becomes a deployment group. So because if you change the schema, you actually would have to deploy all of these functions within a team together. So it's like a group deployment. Now, if you're not changing the schema and if you're changing something internal, keep the interface same, then that's not a problem. But the moment you change the schema of the table, you will have to take this as a unit and deploy this together. So that's a caution that you have to take into account. All right, so now schema change means deployment of entire group. Let's talk about functionality here. A lot of people, and when I look at software architecture in general, I see architecture is a continuous process, right? It's not like you develop an architecture, you implement it, you're done, you're talking about agile, you take the feedback and so on. Same thing applies to serverless computing. You have these functions, right? And typically you want some functions, then you keep adding more and more functions, but you have a resource limit on this. So as you grow, right, functions have resource limits. So as you grow, you basically would increase that. At some point of time, you consume so many resources that it doesn't fit in. So at that time, you would have to split your one function into two functions and then repeat the process. So the point I'm trying to make is your architecture here is evolving. It's not like, okay, I've distributed how my functionality should be distributed on functions. I work on these functions and I'm done. That architecture would change on a continuous process. You would have to split the existing functions into more smaller units. So the key pattern that you want to use is try to distribute your functionality as small as possible. So you have to do this splitting and you have to go through this cycle. You can't avoid it. But what you could do is you can mitigate it. So if you distribute your functionality as small as possible, it's less of these loops that you have to go through. So what that means is continuous refactoring is often needed in such cases. All right. So one of the concerns in the hybrid world, this is probably not the case if you use a managed database like DynamoDB or anything on the Azure side, could be Cosmos DB. But let's say when you have a hybrid world, when you're using traditional database, your functions here, right, they're auto-scaled. So you don't know how the scaling would increase. They're auto-scaled. And what happens is burnout, because so many connections goes to that database, the database cannot handle. You wanna avoid such a burnout. And there are ways of how you do it. To prevent burnout, the first thing you can do is use a circuit breaker. So if I have certain number of connections, it breaks, right? Pretty much how the circuit breaker at home works. If you put a lot of load on the circuit breaker, it will stop. It'll just break the circuit. You can have connection pooling, or the best way forward is to use something like backend as a service, which is managed database. I remember somebody commenting me on this also, and he said you should add something like use a DynamoDB. I was like, if I say BAS, I'm including all the managed databases, right? So those ones are very well suited to prevent such a kind of burnout. So let's talk about event-driven services and eventual consistency. We know that ideally we would like to have in a distributed systems consistency, availability, partition, but the CAP theorem says you can't have all three of them. A distributed system by definition has to have partition, right? And availability is something that we can't sacrifice because downtime is expensive. We need availability. But what we can sacrifice a little bit is consistency. And what we can do is we can change this consistency to eventual consistency. So I have my system, I have my distributed system running across multiple regions, and if I know that my data will be consistent over a period of time, and this period of time typically could be few seconds or few minutes, right? So we are not talking about hours or days. And that's usually okay, because imagine if I'm placing an order on the East Coast in New York, right? And that it takes about few seconds for my order to get updated on the West Coast data center. What's the probability of somebody logging in using my credentials on the West Coast within next 5 seconds? Almost zero. And if it does, it probably means my account is hacked, in which case I would not be worried about consistency in the first place. I'd be worried about security. So what event-driven architecture basically brings to the table here is it gives me a way to have a system which is 100% available and network tolerant, but at the same time eventually consistent. A lot of people, especially in the microservices world, they take microservices and event-driven microservices as synonymous. That's not the case. A microservice is just an application process, application architecture where you have the small fine-grained system. Event-driven architecture is one specific case. It's a subset of the microservice architecture that uses events to communicate and eventually guarantees you an eventual consistency. There are other architectures. This is actually probably the most common, so a lot of people, they think microservices and event-driven microservices is the same. It's not the same. With serverless, you have this event-driven architecture inbuilt because you're talking about functions sending events to each other, right, through the event burst directly. So what you have is you have a system that is eventually consistent, provided you design it well with good availability and partition tolerance. All right. So let's talk about Sagas. We talked about eventual consistencies. Now we need to talk about mechanisms on how we actually have data consistent across different functions, right? So Sagas by definition are long running transactions, and what they have is they have compensating actions to handle failures. The origin of Saga actually happened somewhere around 1987. So if you Google Sagas, you actually would get some paper about databases in 1987, and in those days, obviously, there was no such thing as distributed systems, so they didn't have any concept of partial failures and so on. Sagas were then basically updated, and they're very common. Even in microservices world, they're actually pretty common. And here, basically, what you have is you have, let's talk about an example, right? So I'm going to deposit a check. Saga is basically a sequence of action, right? So this action starts, and then I can have, okay, if I'm going to deposit a check from my account, does the sender who has money has enough money in his account? Sure. It starts a sequence of action. If it does, withdraws the money. If it's not, it's on hold, right? And then it deposits the money. Now, in this case, everything looks very simple. But it's not that simple. So let's actually look at more examples. So you have a transaction and you have a rollback transaction, right? Every action that you do in Saga has a compensating action or a rollback transaction, as I would call it. So, and this logic must be included in your service. So for example, you have a transaction, right? T1, it goes to T2, and T2 is supposed to do the next transaction T3, but what if this transaction fails? You can't do this. What you try to do is you roll back. So you would have a rollback transition. In our previous example of deposit check, say I give a check to someone and the money gets deducted to my account and it's about to be deposited in another person's account. What happens if the other person closes his account? Where does the money go? Well, the money should come back to my account, but what happens is I also close my account. So now there is this floating money that God knows where it go. So when you look at all these scenarios of transactions and rollback transactions in designing your Sagas, there are times when you can get into a really edge cases on how you're going to design. So it's actually not that simple to design Sagas, but it's a very good way of how you can have these, think of these functions communicating with events and having rollback or compensating actions. So that way you can follow an event-driven architecture which will have eventual data consistency, yet guaranteeing you high availability and high network tolerance. So one of the concerns that is often there with serverless computing is vendor lock-in. And part of the reason why this happens is because serverless is relatively, it's not that new, but it's relatively new. I think AWS Lambda came in about 2015, so it's about 3 years, a little more than 3 years maybe. And as a result, what you don't have is you don't have standardization across vendors, right? So if you use one vendor's and you want to move to another vendor, you have to basically work on it. You basically would have to change your code, change your architecture, and so on. So the functionality also is not equivalent across vendors. So you have a vendor lock-in problem here. So serverless technology has benefits, but that benefits comes at a price, and that price is higher migration cost in future. A lot of people generally don't want to move to serverless technology for this very reason. And I'm not sure if that's the right reason, because the way you want to think about it is, if I move to serverless technology, yes, I'm creating a technical debt in the sense when I cross the vendors, I have to do more work. But there's so much of benefit that I'm getting out of serverless, right? So it's basically a trade in cost. It's paying the debt now as opposed to paying the debt in future. And the problem future is no one knows the future, right? So it's harder to plan for something for future. It's easier to plan for something for now. So because I get so much of benefit from serverless, often it makes sense to migrate to serverless platform, even if you're creating a technical debt that the migration cost is going to be in future. And there are a lot of frameworks that actually now are sort of cross-platform. One framework that comes to my mind is serverless. It has a bad name, but it's called serverless framework. So if you Google serverless framework, it basically has a way of abstracting out all the major serverless vendor functionalities. But it's not very successful, and the reason why it's not very successful is when you have an abstraction, what you tend to do is you tend to have a lowest common denominator across vendors, right? Because there are a lot of features that AWS would have that Azure would not have, or Google Cloud Functions would not have. So if you're trying to create a portable code, you can't use those features. So that severely limits you. So that's the reason why, as of now, cross-platform frameworks for serverless technology, they're not very popular. But nevertheless, there's a trade-off. You could potentially use abstraction layer, potentially, but then again, there's a trade-off in the sense that you're probably taking the lowest common denominator. So there's a little bit of trade-off that you have to make. There is a concern, and you have to make your decisions more wisely. Another concern is with serverless is security. Now, what happens with serverless is that you have the kernel, right? And you have the containers, and then you have your container OS, and you have these functions. Now, what you observe in these is these functions share the same kernel. So there is a potential that one function can access another function, and you could have these, running from two different processes from two different organizations. So my code can be accessed by code from some other organization, potentially malicious. So that's kind of a little bit of a problem, but not so much of a problem, because remember, vendor provides you some isolations, and functions are short-lived, and the scheduling is intermittent. So I actually can't really target anybody particular. Let's go with some patterns for large-scale projects. Versioning can be very difficult, and consistency of contracts are needed across. So generally, you could use a monorepo, but the problem with monorepo is practical implementations can be tricky. Another problem with testing functions is it's hard. You could use local executions. Not everybody provides. Azure provides you. AWS, there's a third-party framework that does. Google Cloud does not have. Remote debugging, if it's possible, Azure has it. Monitor the logs, test with curl. There are ways of doing it, but generally, function can be hard. And also, functions can be hard. Also, you have a longer feature cycle, right? If I have to test something, I have to actually develop and deploy and then test it. Whereas when I do local, I can reduce this cycle pretty much very nicely. Some concerns regarding microservices to serverless. Well, there are steps. You can decouple the components, data first to backend service. So that's generally basically a playbook on how, basically a guidebook on how you would move to serverless from microservices, but integrations can often be a challenge. You can lift and shift code too. There are several advantages of using microservices. You can focus on your application code, underlying OS, and everything is all managed. Out of the box auto scaling and load balancing, more cost effective because it's a pay-as-you-go model, but comes with disadvantages. Only asynchronous calls. You have a cold start problem. There's a vendor lock-in because it's not very standard across. To summary, implementing microservices as serverless functions, there are a lot of benefits. The undifferentiated heavy lifting is not there. You have a lot of out-of-box features. Microservices has high management overhead, which serverless can actually help you with reduce it. But most of the real-life systems, they generally tend to be hybrid. At this point, I'm open to questions.
You hear me?
Yeah.
Okay. So basically, what I understand is that we cannot build complete application from serverless architecture, but to use it as an add-on to microservice applications.
It depends on your architecture. So depending on in some cases, yes, not always. They are not. There's no feature parity between serverless and microservices one-on-one. So you cannot get rid of microservices altogether. Now, if you're not using those features that serverless don't have, then yes. So again, it's more of an application specific.
Because with serverless, you cannot have UI, you cannot have synchronous communication, and the communication overhead between functions could be a stopper as well.
Okay, yes. But again, when you go into implementations, right, story is a little different because what the vendor usually would give you is they will give you a way to mitigate all of that at a price. So like Azure has something called Azure App Service. So if you're more interested in a pure serverless, you could potentially look at Azure App Service, which gives you all the benefits that you're talking about.
So you need additional services.
Yeah, but then obviously you don't have, like, it's not so much of a management cost that you're overhead, but it's now you're not having a pay as you go. So it's not a cheap, right? It's an always on service. So you will have to pay for it whether you use it or not. So you can mitigate those disadvantages for a price that if you're willing to pay for it.
Okay, thank you.
There's one question there.
Thanks. My question's about the different. So the question is about how you break up the system with microservices. One way you might approach that is to figure out the boundaries between your domains and make those microservices. Or if they're still huge, you could break up the domain in a way which reduce the amount of chatter, or minimize the amount of chatter between services. For example, then so that's one way you could approach your microservices, and then the resolution for serverless would be functions. So could you talk about your experience reconciling those different levels of resolution?
Yeah, so usually domain-driven design is often a more standard practice for that. That gives you basically, more particularly aggregates in domain-driven design, they basically give you the seam across which you can partition. Now, domain-driven design is pretty much, very much used in microservices also for the very same reason of splitting up the functionality, right? So you could potentially use domain-driven design also in a serverless application for the very same application. The only, for the very same reason of, splitting your, distributing your functionality. It's a little tricky though, because remember in microservices, you don't have a resource limit problem. So certain processes that are long running, you can still have them as microservices where you can't have them as serverless functions. So if you run into that, then you probably don't want to use serverless for that particular functionality. And this is where again it gets tied up. Most of the real life systems tend to be hybrid, right? But a short answer to your question is domain-driven design would basically provide you, the aggregates in domain-driven design would provide you basically the partitions on how you want to split up your functionality across functions or across teams. Do you have an additional question on that? I can expand on it.
I'll ask you about your experience of how you.
The thing is, this is a very tricky question because it's a little bit of art and not science kind of thing, right? And it's very application specific. So, I mean, I've used it. I actually worked on a lot of kiosk tools. So we used a combination of Azure App Services and Azure Functions for that. For the applications we used, somehow the partitions were very clear. But again, this is a very application specific. So I don't really have a general answer to your question. Yes, please.
It's a question sort of around overengineering and when to sort of draw the line about using serverless. So say you've got an application that essentially creates your customers, and then you've got a third party where you've got to also create their customers. And say that process is asynchronous for creating it with the third parties, and you've got that actual process running on in the same microservice, just as sort of like as a asynchronous process.
Yeah.
would you think that that is an appropriate time to use it, or is it sort of just using it because you can, if you know what I mean?
I usually like to go with, if I'm switching to a new technology, what's the benefit I get, and revolve around that. My key point is that with microservices, there's a management overhead that serverless can reduce. So the first question I'm going to ask myself is, how much is that overhead? If it's not a lot, and if I have a system working in microservice, why bother?
Yeah.
Right? It's like we don't use technology for the sake of using technologies. We use technologies because it helps achieve certain technical and business goals. So you have to look at it from that point of view. What is the benefit? I am putting more effort migrating a microservice to serverless, and I'll have n number of issues, unforeseen issues that I have to do. Is it worth wasting my time on that if I don't get a benefit out of it? Maybe not. Maybe. Any more questions? Yes, we have one there.
You've given a really good overview of the benefits and disadvantages of both of the routes, I guess you could take. Is there any success stories where functions have actually can be shown to be a better solution than going with the microservice way?
Yeah, it's hard to answer that question. And the reason why it's hard is, first of all, serverless is a new technology, right? It's not very mature, that it hasn't really, I mean, production systems are using it, but it's yet to prove itself, right? I mean, people are right now talking about moving from monolithic to microservices, and you're talking about one level up, right? So it's a little premature to answer your question. And secondly, see, most of the systems tend to be hybrid. So you can say that, yes, I get benefit from serverless, but you get benefit from both, right? It's hard to say, well, serverless is good, microservice is bad, because I'm trying to use both. It's most of the systems that there might be several systems that you're running that's talking about microservice and using some kind of serverless in the background that you may not be aware of. So there are success stories, yes, that use serverless, but usually most of those success stories use both serverless and microservice, and it's hard to say, well, I am successful because I use serverless and I migrated from microservice to serverless, and yes, we are not at that stage yet. It's still premature to answer that question right now.
Time for one more.
Last questions, if any. We have one question here.
So this is about more of a question / comment on what the gentleman asked earlier as well. We talked about a lot about the management overhead saving of moving to or doing things in a serverless architecture, but didn't quite touch on the fact that the potential more processing power you can get for the same operational cost or less operational cost, because if you have batch function or something that you want to run once a day or something, that would be the ideal candidate to have a serverless architecture, and you can get more computing power, you can scale up, and then you can die out. Is that something that you feel that is not a benefit, or is that just uses?
It is a benefit, but you talked about more computation power, and I want to emphasize that a single serverless function has a resource limitation. Right now, if you're talking about functions put together, yes, obviously I have n number of functions I can auto scale. Batch processing generally is one of those things where serverless actually fits quite a lot. But what he talked a little more was more about moving from migrating to serverless. Now, if you're designing a system from scratch, that's another thing as migrating, right? Migration has an headache. So if I was to design an application, I would totally use serverless in your particular application. But if it's already running in a microservice, then I'm asking myself, is it worth moving or not? Right? And that's where I want to emphasize, you really have to do a cost-benefit analysis of it.
Thank you.
All right, thank you.